Progress.
Hello, Sharon.
Good evening.
Good
Fine.
evening. Hello, Lokesh. How are you? Hi, Sharon. How are Fine? Everyone good? Right? Okay, let's start now. Okay, so we were discussing about the electric potential, isn't it? So let's continue now. Hi, Shashant. How are you? Now, is it okay? Fine. Now, let's continue now. Okay. So we were calculating the electric potential, isn't it? And the conservation of energy we have discussed. Okay. The electric potential we have calculated due to the uniformly charged ring. Okay. At the center we have calculated and on the axis we have calculated. Okay. Right. At the center the potential was kq by r, where q is the total charge on the ring. And on the axis we got it kq by under root of r square plus x square, where x is the distance from center to the point P where we are calculating the potential. Okay. Next, we have discussed some questions on the energy conservation. Okay. Then we discuss electric potential due to what? A circular arc at the center. Okay. So how much we got it? KQ by R we got it. Then we calculated due to line charge or the thin wire. Okay. 2 points we discussed. One was the along the wire We got a very simple relation, okay? And perpendicular to the wire, there was little bit integration needed, okay? So this perpendicular to wire, very few questions you will get it due to the finite wire, okay? Perpendicular to the wire, mostly the question will come because of the infinite wire, okay? So let's calculate what is the electric potential due to infinite wire. But before doing that, we should learn one thing that is called relation between the electric field and potential, okay? Because that relation is potential due to what? Due to a spherical charge distribution, okay? This relation will be very much needed, okay? So relation between electric field and electric potential, okay? Relation between electric field and electric potential, okay? Let's discuss that one. So what is the relation between the electric field and potential? Let's try to understand, okay? So field and potential relation, if we try to find out, tell me, what is the relation between the potential energy and the force? Do we have the relation? Please tell me. We can write it change in potential energy. Is it equal to work done against the conservative force? Can we write it like this? Please tell me. Change in potential energy. Can we write it? Work done against the conservative force. We can write it, isn't it? Please tell me. Is this part is clear? Please tell me. This part is clear. Change in potential energy due to any kind of conservative force can be written as delta U equal to minus of work done by conservative force, isn't it? So if you are writing here, see, here again the same thing. We are writing change in potential energy. Can we write it? It is going to be negative of small amount of work done by conservative force, and the conservative force involved here is nothing but the electrostatic force, which is the conservative in nature, isn't it? Now tell me, change in potential energy, can it be written as charge into change in potential? Please tell me. Do you remember potential we have defined as potential energy per unit charge, isn't it? So change in potential energy can be written as charge multiplied by change in potential through which that charged particle has moved, isn't it? Minus. What is work done? Work done can be written as force into displacement. And we are discussing here the electrostatic force. Electrostatic force will be how much? Charge multiplied by electric field into what? A small displacement, let's say something dx happened, okay? So if you see that charge and charge got cancel out here, so do we have, and you can also write it here, the vector symbol e dot dx. So what we have here, if you check it carefully, can I write it? Dv equal to minus of e dot dx. So this is the relation between what? The field and potential. This is the relation between what? The field and potential. So sometime what will happen? Field in a region will be given to you and you have to calculate the potential difference. So what will be potential difference? dV equal to minus of E dot dx. And sometime potential will be given to you and then they will ask you the electric field. So how much we can write it? The electric field will be minus of dV by dx also. So this dV by dx, you know what is this dV by dx called as? dV by dx is called as the potential gradient. Okay, dV by dx is called as what? The potential gradient. Okay, is that clear? So what is the negative sign representing here? So negative sign here in minus dV by dx represent what? The direction of electric field. And what is the direction of electric field? So direction of electric field is always from high potential to low potential. Okay. So direction of electric field in a region in a region is what direction? Is always from high potential to low potential. Understood? So in a reason, if I know these are the 2 points given to us, and then they ask us to tell me which point is high potential and which point is low potential, then by looking at the direction of right uh, field, we can say which is the point at high and which point is at the low potential. Why? Because electric field in a region is always from which direction to which direction? High potential to low potential. Understood? Please tell me. Clear up to this? So
Yes.
from field, yeah, please tell me. Please tell me. Any question up till now? What we discussed?
No, sir.
Right. So if electric field is given in a region, we can find the potential difference. And the second thing, if potential is given, then we can also find out what will be the electric field in the region. And if you want to decide the direction of electric field, always look at the potential. The point which is at high potential and the point which is at low potential, the field will be always in which direction? Always from high potential to low potential. Okay, so let's see the two example where we are going to use these two concepts. Okay, please keep in mind these two are the very important part. That means potential calculation with the field or field calculation from the potential. Okay, let's see some examples, or you can say some of the application of these two. Okay, so what is the application? Let's say, see, whenever we have infinite charge distribution, we never calculate potential, absolute potential at a point. What we calculate actually, we always calculate the potential difference between the 2 points. Understand? The reason is what? See, when we write now potential is kq by r, right? We have written the potential due to a point charge as kq by r. So when we write that thing, what we do, we consider potential at infinity to be zero. But if an infinite charge distribution is there, then what will happen? Potential at infinity cannot be taken as zero. So that's why what we should do whenever we calculate the potential due to infinite charge distribution, we should always calculate the potential difference between the 2 points, not the absolute value of potential. Okay. So let's see. Let's say I'm calculating potential. Potential, or should I calculate potential difference? Please tell me. Potential difference between the
2 points.
2 points, 2 points due to infinite line charge or long linear charge distribution. What is the potential difference between the 2 points we are going to calculate? So let's say there is an infinite rod given to us. This is the infinity extended. This is also extended up to infinity, and this is also extended up to infinity. Okay, and this has the charge distribution like this. Linear charge density is something lambda given to us. Lambda is the linear charge density. Now there are 2 points given in this question. This is the point 1. This point is r1 distance from the rod, and there is another point. Let's call this point is 2. That point number 2 is r2 distance from the wire. Can you tell me which point is high potential? Point number 1 or point number 2? Please tell me which is high potential, 1 or 2? If I just ask you theoretically, don't tell me the value. Just tell me which point is high potential, 1 or 2? Please tell me what will be high potential point, 1 or 2?
2.
1 or 2? 1, na? See, what is the direction of electric field here?
Yes, Abhima.
Is this the direction of electric field?
Yes.
So electric field is in towards right, isn't it? So if you see the point number 1 and point number 2, is the field of is from 1 to 2? And what is the direction of field? Direction of field is from high potential to low potential. Okay. So here what will happen? V1 will be greater than V2. Understood? What will happen here? V1 will be greater than V2. Okay. So point number 1 is high potential. Point number 2 is low potential. Now let's calculate what is that potential difference. Understood? So if I want to calculate the potential difference, what I will do, I will start with what? The field. Let's say there is a point here, which is how much distance? Let's say there is a point, some x distance from the wire. Where is this point? That point is some x distance from the wire. So can you tell me what will be field at a distance x from the wire? The field at a distance will come lambda by 2 pi epsilon naught x. Can we write it? Field at a distance x will be how much? Lambda by 2 pi epsilon naught x. And let's say some dx distance is there. So can I write it? dv will be equal to minus of E dot dr. And here field is variation. Field variation is with x. So can I write it? E dot dx we will have. So dv will come here. How much? Minus. What is the electric field? Lambda by 2 pi epsilon naught x. And then we have dx. Let's integrate it. Now tell me, what is the point where I want to find the field? We want to find the potential difference between the 2 point 1 and 2. And where are these 2 points? The point number 1 is at R1 distance. So can I put it? When x is R1, potential is V1. Please tell me. When x is R1, potential is what? V1. When x is R2, what is the potential? V2. Isn't it? Now let's integrate it. The dv integration, v will come. Limit if you keep it, v2 minus v1 it will come. Minus outside, lambda outside, 2 pi epsilon not outside. Look at that. Dx by x integration. Dx by x integration, how much it will come? Ln x will come. Right. Upper limit if you put it. So R2 will come. Lower limit if I put it. R1 will come. And if you send this minus other side of the equation, what it will become? V1 minus V2 equal to lambda by 2 pi R1. Please check it. Understand the potential difference between the point 1 and 2? So that's why please keep in mind whenever it is given in a question that the infinite line charge is there or infinite sheet is given to us and we want to calculate the potential difference, what we should do? We should always take help of what? dv equal to minus of E dot dx to calculate the potential difference. Is that clear? So potential difference between the 2 point 1 and 2, which is R1 and R2 distance from the wire. Okay, R1 and R2 perpendicular distance from the wire. What will be the potential difference between these 2 points? Lambda by 2 pi epsilon naught ln R2 by R1. And please keep in mind the field will be always in the direction of what? High to low potential. So sometimes theoretically they will just give you the direction of field lines. Okay, and then they will ask you which is high potential and which is low potential. So keep in mind the field is always from high to low potential. Is that clear? Next we are going to calculate the potential difference due to infinite sheet. Again, the moment I said infinite sheet, that means instead of calculating the potential, we will calculate the potential difference. Please tell me, clear up to this?
Next time will they ask these derivations and all?
No, derivation, why we are doing that? So that you will keep in mind that how we are going to apply those.
I mean, sir, those FRQ questions, like the long answer questions.
Long answer questions they can ask you. Long answer question they can ask you, or sometime what they will do, they will give the lambda is not a constant one, lambda is a variable one. In those cases you have to start from the basic, right? You have to start from the fresh equation where it comes from.
Are there any standard type of questions? I mean, the standard derivations.
No standard derivations, no, not like that. But I checked some of the questions they are starting from the uh, fresh one, like they will give you the statement, right? And they want us first to find out what is the formula we are going to use it in that question. That formula we have to get it from the starting definition of that particular thing. Okay, so yes, in the that second section is there na, long answer questions. There it may be possible that you have to show the derivation also. Okay.
Are there any important questions like this is Pakka?
Im- Important questions of questions, so we cannot guess it now, right? So that's why we are preparing everything. We will discuss the previous year questions also. There you will see that what is the uh, patterns, what are the questions which is repeatedly asked. But if you ask me to guess four questions from the entire syllabus, then that no one can guess, isn't it? Right?
Yeah.
That's why we should focus on all the concept, right?
Yes, sir. Yes, sir.
Right. So potential difference between 2 points, we are going to again calculate it. Okay, between 2 points, and this time I am taking due to infinite sheet. What is the field due to infinite sheet we got it? What is the field we got it due to infinite sheet? If infinite sheet means surface charge distribution will be there, isn't it? Surface charge distribution.
I came to Saudi.
So field we got it as what? Sigma by 2 epsilon naught, right? And again I'm going to take this point is 1, this point is 2. Point number 1 is r1 distance from the sheet, and point number 2 is what? R2 distance from the sheet. Please tell me, what is the field? Is this the direction of field? If I'm talking about right side of the plate, that is the direction of field. Again we know that which point is high potential, 1 or 2?
One.
But 1, right? And what is the potential difference will come? Again we should use it what? dV equal to minus, what is the field? Field is sigma by 2 epsilon naught, and dx, isn't it? Let's integrate it. When x is equal to r1, potential is v1. When x is equal to r2, potential is v2. So we got it, v2 minus v1 equal to minus sigma constant 2 epsilon naught constant dx integration x, and that will come r2 minus r1. Send the minus other side, it becomes v1 minus v2, and that is equal to sigma by 2 epsilon naught. And look at that, r2 minus r1 is what? Is the r2 minus r1 is nothing but the separation between the 2 points, isn't it? Separation between the 2 points 1 and 2 also. So you can also write it here, v1 minus v2 equal to sigma by 2 epsilon naught into separation between 2 points also. So sometime it may be possible that they don't mention the actual distance of r1 and r2 from the sheet. They will just give you what? The separation between the 2 points they will give you. Okay. Why? Because here the potential difference is not depending on what is r1 and what is r2. Potential difference is depending on what? The separation between the r1 and r2. Okay. So be careful about the question when we get this kind of. Okay. Clear? Now, sometime we have to calculate a point which is called equipotential surface or line which is called equipotential line. Can you tell me what does it mean by equipotential surface or equipotential line? What does it mean by equipotential surface
Either every
or
point
line?
on that.
Yeah, please tell me equipotential surface or equipotential line. What does it mean?
On that line will have same potential.
Yeah, it is a surface or it is a line, right? Where every point are going to have what? The same potential. Understood? So if I say, tell me an equipotential surface for this sheet, can I say that if I make a plane here, check it, is every point on this plane, right? Just a plane parallel to the sheet will have everywhere the same potential. Can I say that? Same way, if I draw a plane containing the point number 2, containing the point number 2 and parallel to the sheet, will it have the same potential? Right. So equipotential surface is that. Same thing here. What kind of surface will be equipotential surface? If it is an infinite wire, so can I say that if I make a cylindrical surface enclosing the wire, can I say that surface is going to be an equipotential surface? So equipotential surface, theoretically you can say, what does it mean by equipotential surface? Equipotential surface means what? A surface, where every point, what is an equipotential surface? A surface where every point on the surface has what? Surface has same potential. Understood? Surface has what? Surface has same potential. Is that clear? And you will be seeing a very interesting thing about equipotential surface. You see that, can I say equipotential surface is a surface where the electric field is perpendicular to the surface? Check it and tell me. Can I say equipotential surface is a surface where the electric field will be perpendicular to the given surface? So if I can identify a surface where the electric field is exactly perpendicular to the surface, then that surface will be what? An equipotential surface as well. Okay, so equipotential surface has two meaning. Okay, what is the first meaning of equipotential surface? A surface where every point on the surface has same potential. And the second meaning of equipotential surface is what? That it is a surface, mathematical way. First one is the theoretical explanation of equipotential surface. Second one is what? The mathematical one. Mathematics says what? That an equipotential surface will be that one where if where on the surface the field is always going to be what? Perpendicular. Okay. So a surface where electric field where electric field is perpendicular to the surface will be called as what? Equipotential surface. Understood? An equipotential surface, I must look at the surface in such a way that the surface field will be what? Perpendicular to the surface. Okay? Clear up to this? Please tell me. So equipotential surface or equipotential line. Line means what? Sometime it will form a line. Means every point on that line has what? The same potential. That line will be called as what? Equipotential line. It will be also called as. Is that clear? So equipotential surface or equipotential line is what? A surface or line where the potential is what? Same at each and every point. Is that clear? Please tell me. All of you are clear? Please tell me. Everyone
Yes, sir.
clear what we discussed till now?
Yes, sir.
Please tell me. Lokesh,
Yes, sir.
Sushant, Charan.
Please.
Right. So clear. So equipotential surface is a surface where potential or every point on the surface will be in such a way that it is going to have what? The electric field always or 100% what? Perpendicular to the surface. Clear? So that's why what happened. Next thing we are going to discuss is going to be the potential calculation due to two type of charge distribution: a spherical charge distribution, where the charge is what? One case uniformly distributed on the surface, and the second case throughout the body. Okay, so let's calculate electric potential due to. Okay, the next calculation we are going to have. After that we will discuss some example now, but before that let's finish it out, the two of them. Electric potential, okay, due to what? Hollow sphere. Please tell me, hollow sphere has another same thing. Can you tell me what is that? Hollow sphere or shell, है ना? Hollow sphere or shell or what? Can you tell me one more name? Hollow sphere or shell, it has the same property as that of
Conducting solid.
yes, conducting solid. All three situation, the charge is only going to be what? Distributed on the surface. We cannot have what? Charge inside a hollow sphere or a spherical shell or a conducting sphere. The moment it is said, whether it is a hollow or solid, it is always going to behave like what? The hollow. A conducting sphere cannot have the charge inside. If it is a hollow or solid, any of the case. Okay, so let's calculate the electric potential due to this kind of arrangement. Okay, so please tell me, if I give you there is a spherical shell of radius r, where is the charge distributed? Charge is distributed only sphere. Okay, how much charge is distributed? Let's say q charge is distributed. R is the radius of a sphere. Now please tell me, how many important point we have. Do we have the two important point? The first one, capital small r greater than or equal to r. What does it mean? That means we are calculating for outside point where what is the potential. So please tell me, what will be the potential outside the sphere? And whenever you are calculating the potential or field, anything, but you are calculating due to a spherical distribution, what will happen? You should always measure the distance from where? Distance from the center, isn't it? We always measure the distance from where? From the center of the sphere. The outside point, how does the charge distribution look like outside the sphere? For outside case, is the charge distribution is less like a point charge placed at the center of the sphere. So that's why for outside point there is no problem. It will be just behave like the entire charge is accumulated at the center. The outside point, what will be the potential? Just kq by r. Is that clear? Can you tell me what will be the value on the surface? Is the surface potential is going to be kq by capital R, isn't it? So potential
Yes.
for outside point. Let's say I want to. calculate here. So I will just write it K, what is the total charge on this sphere, divided by what is the distance from center to that point. Clear? But surface KQ by capital R. Please tell me the second part. If a small r is less than capital R, does that mean now I am thinking about if the point is lying inside the sphere? Please tell me what is the potential inside.
KQ by capital R.
What is the potential inside? K capital Q by
Capital.
capital R, same as the surface, right? What is the reason? The simple reason is what? If you look at inside, what is the field inside we have calculated? What did we calculate? The field inside a conducting sphere or a hollow sphere or a solid conducting sphere or shell. We got the field inside a conducting sphere or hollow sphere as 0. Now you tell me, what does it mean by field 0? You have field equal to minus dV by dr, isn't it? Now what I can say about the V? Can I say the V will be constant? That means because a constant differentiation only comes as 0. Conducting a sphere will have what? The same potential. So what will be that potential? So whatever is the surface potential, the same potential will be what? Inside the conducting sphere, every point is 0. And what is that value? Sorry, not 0. Field is 0. What is the potential inside a conducting sphere at any point? It is same as the surface value. So inside point and surface point will have the same value. And how much is that? KQ by capital R. So now if I want to plot a graph, okay, let's say I want to plot a graph of potential versus distance. Potential versus distance. Distance I am going to always measure from where? Right? That is what we have made our from the starting only. Na? Whenever the spherical comes, we always measure the distance from the center. Tell me what kind of graph will come? See, can I say the graph will be constant? Till what time it will be constant? Till the small r becomes equal to capital R. Means what? Till I always constant and equal to KQ by capital R. And once I reach the surface, after that, will it start decreasing inversely proportional to what? So KQ by small r we can write it. And surface it remains constant. And when we are going outside point, the potential will become what? Inside point. Can I say inside point potential is constant and inversely proportional to distance from the center? Now, if I'm asking you a theoretical question, what kind of equipotential surface will be outside the sphere? Tell me, outside the sphere, what kind of equipotential surface will look like? How equipotential surface will look like? Please tell me. If I am asking what is the equipotential surface for a spherical charge distribution, please tell me how the equipotential surface will look like. If I say outside, I want to say, can I say outside it will be what? A spherical with
Spherical structure.
concentric with original sphere or charged, है ना? A spherical concentric with charged sphere. And inside what it will be? Now you are going to get an interesting answer. What kind of equipotential surface will be inside?
Same
Any random surface.
potential only, right?
Understood? Can you tell me why? Why inside any kind of surface? Any random surface, I draw it inside. Can you tell me this is equipotential surface? If the point is inside? Yes,
Yes.
why? Look at the point. Take any point on this surface, you will find out same potential, isn't it? So that's why for a hollow sphere or a spherical shell or a conducting sphere, if I'm asking what kind of equipotential surface outside will form, then outside it will be also spherical in nature, concentric with original sphere. But if you are calculating for inside point, what will happen? Any random shape you want, you can draw it, and it always act like what? An equipotential surface. Is that clear? The last one we have is for solid non-conducting sphere, where the charge distribution will be inside as well as throughout the body. Okay. So here little bit calculation will be there. Please don't fear about it. It's just going to make you learn something about the question. Okay. Please tell me, little bit calculation will be there. You want to do it? Something extra we can study now, so that if any difficult question will come, you will be able to answer it, isn't it? So solid, next one what we have? Potential due to solid non-conducting, है ना? Because the moment I said solid, I must mention it. Is it a conducting or non-conducting? Because if it is a solid body, but still if it is a conducting, it is just going to behave like a conducting sphere, hollow sphere. Okay, na? So that's why if it is a solid, I must mention it. It's a non-conducting sphere, so that I can give you the charge distribution inside uniformly. Okay. So uniform charge distribution I am taking. Okay. And again, I am going to calculate it at the 2 point. Here, what will happen? What kind of charge distribution will be there? So here, the charge distribution will be throughout uniform charge distribution. Okay. I'm going to take uniform charge distribution. Okay. Let's say this is the center, right? Radius of this sphere, original sphere is what? R. And we have given what charge? Q charge on what radius? R radius. Can you tell me what is the charge density? Is the charge density is charge divided by per unit volume, Q divided by 4 by 3 pi r cube. Understood? Now again, we want to calculate the potential. Again, how many points will come? There are going to be 2 points where I'm going to calculate the potential. Is that clear? The first point is going to be small r greater than equal to capital R. What does it mean? That means my focus point is what? Outside the sphere. My point is where? Outside the sphere. Now you see, outside the sphere, the charge distribution will act like as it is just like a point charge kept at the center. So what is the potential outside? The outside potential is still kq by small r. Understood? Where small r is the distance from center to that outside point. What is the value on the surface will come? The value on the surface will come kq by inside. That is an interesting calculation. Tell me, what is the potential inside? Because if a question will come on the solid one, then they will ask you for inside point. So tell me, what is the potential inside? Please.
So the formula.
Yeah, a big formula is there. K
Yes.
cube by 2r cube 3r square minus r square, something like that, isn't it? Right. Let's see how that came. Okay. Just I'm going to give you. See, tell me, how do we write the potential? Can we write potential equal to dV equal to minus? What is the field for a point lying inside the solid non-conducting sphere? What is the electric field inside a solid non-conducting sphere? Anyone remember? It was KQ small r by r cube. Do you remember? Field inside a solid non-conducting sphere was KQ small r by r cube or rho r by 3 epsilon naught. There are two ways we have derived, or not two way, we have derived one equation using the Gauss law, and then if I want to write it in terms of density, I will use it rho r by 3 epsilon naught, and if I want to write in terms of charge, then I will use it capital Q and capital R, right? So out of these two, you can use any one of them you want, okay? So I am going to use what? Field is KQ small r by RQ into dr. Please tell me, is this the dV clear to you? Please tell me, is this the dV clear to you? The definition of dV E dot dr is there, isn't it? And we want to calculate the potential difference for a point, potential difference between the 2 points lying inside, isn't it? So I should use the field inside, isn't it? So what is the electric? It is KQ small by RQ, right? Or rho r by T epsilon naught, whichever you want, you can use it. Now we will calculate it. Please tell me, when a small r is equal to capital R, what is the potential being as the capital R? And when the distance is a small r, a variable distance, what is the potential? I have to calculate, simplify it. dv integration v will come. If I keep the limit v minus kq by r, it will become equal to minus k constant, q constant, r cube constant. And then we have r dr integration, that means r square by 2. The r square by 2 minus capital R square by 2. Please tell me, clear this one? So v minus kq by r, what we have here, send it inside this minus and then simplify it. Am I getting kq? Please check it. Kq 2 outside, isn't it? Kq by 2 r cube outside. Kq by 2 r cube outside. Do we have capital R square minus small r square? This minus I have sent it inside. So let's send the kq by r other side. So kq by 2r cube r square minus small r square plus kq by capital R. Just simplify a little bit and we will get our answer in the desired format. Okay, so kq by 2r cube into 3r square minus small r square. So from here, if I want to calculate what is the potential at the center of a solid sphere, we will put it a small r as what? 0. And if we put a small r as 0, what is our answer coming? Is it coming 3 by 2 kq by r? So that's why if you see the potential at the center of a solid sphere is 3 by 2 times the value on the surface, isn't it? Potential at the center is what? 3 by 2 times of the value of potential on the surface of a solid sphere. Please check it. Please tell me, are these points are clear? So now if I want to use it again, please tell me, see that and tell me potential distance from center. Tell me, can I say initially what is the value at the center? The value at, and when I reach the surface, the value becomes what? When we reach the surface, the value becomes kq by r. And please tell me, for inside point, what kind of graph will come? A straight line, rectangular hyperbola, or just a parabola? Please check it. Kq by, these are constant, isn't it? V is minus r square proportionality. So it means for the point lying inside, the graph is going to be a parabola. And once I reach the surface, then onward, what will happen? The graph will become a rectangular hyperbola. Understood? This is what distance? This is the distance when I reach the surface. Understood? So here, if you look at the graph for inside point is parabolic, and graph for outside point is what? Hyperbolic. Okay. Parabolic means quadratic kind of. Quadratic equation is a parabola equation, and a hyperbolic means inversely proportional to distance or inversely proportional to distance squared. These cases are called as what? Hyperbolic one. Is that clear? So please tell me here one thing. What kind of equipotential surface we are going to get it? Can I say that for inside point also it is spherical, and as well as outside point also it is what? Spherical, concentric with the original sphere whose charge distribution is given in the question. Understood? Please tell me. So when we find out equipotential line due to solid non-conducting sphere, it will be what? It will be a spherical in nature for inside point as well as the outside point. Please tell. Clear up to this?
Yes.
Please tell. So now we will discuss few questions on these topics. Okay. Potential difference calculation. Understood? And please keep in mind, whatever we have done, these two different derivation you can call it, or the concept we have learned it, these two are going to help you in calculation of what? In calculation of the capacitor. Because when we will calculate what is the capacitance between the two parallel plate, you will see that this potential difference will be required. Potential capacitance of a cylindrical capacitor. Again, this potential difference of the cylinder, you can say that, or wire, you can say that, that will be required, right? In case of spherical capacitor, we will need the potential difference between the this conducting sphere will be needed. Okay. So although these are looking like just the derivation, but these derivations or these concepts are going to help us in further calculation. Understood? Now let's just one example I am giving. I will discuss more example on this one in tomorrow's class. Just one small example I am giving to you, and we will continue from here. Just one example. There is an infinite wire given to us. Okay, a very long wire given to us. It has a charge distribution of what? Something lambda. Okay, some charge distribution is what? Lambda. And tell me, if I release a particle from here, what kind of particle? Particle of mass m, charge minus q. What will happen? Is this particle is going to be attracted towards this wire or not? So this is the initial position of the particle. And when they are saying initially, where is the particle? Initially, the particle is 2r distance from the wire, and when the particle reaches r distance from the wire, so you have to tell it will be attracted towards the wire. Na? Please tell me. So they are asking in the question, find the velocity of charged particle. Okay, what we have to calculate, velocity of charged particle find the velocity of charge particle. Okay, from when the separation changes from 2r is 2r distance from the wire. Now it has become r distance from the wire. So what is the velocity of this charge particle? That is what they are asking in the question. What we should do it? Please tell me. Can I again apply the energy conservation in this process? Please tell me. Please tell me, can we apply the energy conservation in this process? So
Yes, sir.
K initial plus U initial, can we write it like this? K initial 0. U initial means, can I write it? U initial means charge into V initial. K final means half mv square. And U final means charge into V final. Coming charge multiplied by V initial minus final. And what is the potential difference between initial and final? Please tell me. If I ask you here, what is the potential difference? Which is high potential? Final is high potential or initial is high potential? Is this the direction of field?
Final
Look at the direction of field. The field is towards right. Yes, the final is high potential and initial is what? Low potential, right? Because look at the direction of field and we can say that high and low potential. Okay, the final point is high potential, initial point is low potential. Understood? So now if I want to just find out that potential difference, that is what we have calculated. How much we will get it? Lambda by 2 pi epsilon naught ln, right? R2 by R1, isn't it? So V final minus, this is the field direction, and the V final minus V initial will come lambda by 2 pi epsilon naught ln. R2 is 2R, R1 is R. Now just put that value, half mv squared. What is the charge? Minus q. What is the V initial minus V final? That is minus lambda by 2 pi epsilon naught ln 2 we have. Just simplify it further. Minus minus got cancel out. So what is the velocity we have? 2q lambda by 2 pi epsilon naught m ln 2 square root of that. Please tell, clear up to this what we discussed?
Yes, sir.
Please tell me, clear? Right? So
Yes, sir.
tomorrow we'll discuss few more questions. Okay? Right? Please tell me, clear up to this. So let's continue with some example tomorrow also. How the distribution of charge will take place when we will connect the two conductors. That we'll discuss it in tomorrow class. Okay? So let's meet it tomorrow. Right, everyone?
Yes, sir.
Yes.
Thank you, sir.
Thank you, everyone. Take care and let's meet it.
Thank you, sir.